awards, and I know I actually try to count them and put them maybe in an Excel sheet to get the right number, but I think you're approaching like 3 digits. So you also are the author of a classic, which is the Introduction to Signal Detection and Estimation. So I think everyone knows of you, who knows you. So we're really, really happy to have you here and give a keynote talk. And I'll hand over to you right away. I know you have a PhD defense on the hour, so we may just be able to squeeze that in.
Okay, thank you very much, Reinhard, and good morning, afternoon, evening, everyone. Let me get my slides up here, and then we'll get going. Here we go. Let's see. Let me get it going here. Can you see me? Can you see my slides, Reinhard?
Yes, perfect.
Okay, great. Well, let me get started then. First of all, again, thank you, Reinhard, for that introduction, and thank you all for attending my talk. It just snowed. We had a big snowstorm here in the East Coast last night, so I'm snowed in. So it's a perfect time to be giving a talk over Zoom. Dr. E just told us a lot about how AI is going to be used in wireless networking in the future, and 5G, and of course transitioning to 6G. And I'm going to talk about a different aspect of that, which is the use of mobile networks as a platform for machine learning. So it's the counterpart to some of the things that Dr. E talked about. So I'm going to try to be relatively quick here. As Reinhard said, I have a 9 o'clock East Coast defense. It's actually in Germany, so it's on your time. Again, there are two aspects to the combination of machine learning and wireless communications. One is using machine learning to optimize communication networks, and Dr. E discussed this in depth, and I think you saw how the great opportunity there is for that type of connection between machine learning and communication networks. The counterpart, which I'm going to talk about now, is the use of mobile networks as platforms for machine learning, as I said before. So I'm going to talk about that. Hopefully, it'll take about 30 minutes of your time this morning. So here's the outline of my talk. First of all, I'll motivate it a little bit. Then I'll talk about two things. One is federated learning. The other is decentralized learning, and I'll describe the difference in these two shortly. And then I'll wrap up with conclusions, and I'm going to talk about some open issues. And like Chi Lin's discussion, I mean, some of this is 5G, some of it is really looking forward to 6G. But I think for today, we can think about this as being something that could be implemented over 5G networks. So let me motivate things a bit, and I'll start by giving a fairly oversimplified view of the state of the art in machine learning. So obviously, this is one of the most rapidly growing fields today. Machine learning is not new, of course, it goes back decades, but what's happened in recent years has been the availability of much more data, as Chi Lin mentioned, and also a significant increase in computational power everywhere in the network, in the cloud, and so forth. So sort of a standard machine learning paradigm is that the machine learning is implemented in a centralized manner in the cloud or at a data center with full access to the data. And this gives rise to state-of-the-art models such as deep neural networks that run in the cloud. And of course, this can be managed by standard tools like TensorFlow and their special hardware, NVIDIA GPUs, Google's TPUs, and so forth. So this is, like I said, a very oversimplified, perhaps, view of the state-of-the-art in machine learning today. Now, this kind of centralized machine learning might not be suitable for a lot of applications involving mobile networks. For example, self-driving cars, first responder networks for emergency situations, healthcare networks where There may be healthcare data involved. And these applications are different from some of the others that we might consider for various reasons. One is, first of all, the data is born at the edge. That is, data is born in iPhones and IoT devices. In a mobile network, of course, the uplinks are of limited capacity. So this makes it more difficult to upload data all the way back to the cloud. Oftentimes, these are time critical applications, so low latency is important and high reliability, certainly for healthcare and self-driving cars. Privacy and security are big issues. Again, this is particularly for healthcare, for example. And then scalability and locality, that is, for example, for autonomous driving, we're really interested in what's happening in our local neighborhood. We don't really care that much about what's happening elsewhere. So that, you know, if we can do machine learning away from at the edge rather than in centralized manner, we can accomplish what goals we need to accomplish. So all of these factors motivate moving learning closer to the network edge. So I'm going to talk about two models for this. First of all, the model I just described as the sort of standard machine learning model, we can think about it as a model where data is collected at the edge, uploaded to the cloud, models are derived in the cloud, and then distributed back out to end user devices. Now in federated learning, I think most of you are familiar with this, but the end user devices collect data. The data is retained on those end user devices where a common model is learned at the end user devices. Those models are shared at an aggregator, which could be an access point or base station. And then the aggregated model is returned to the end user devices where it can be updated, and this process can be iterated. So the data here is retained on the end user devices, which are performing machine learning themselves. And then finally, a decentralized machine learning model, there is no aggregator. We only have end user devices. Communication is peer-to-peer, and they may be learning a common model, but they're doing that by sharing model parameters or data locally in their communication range. So I'm going to talk about the latter two, federated learning and decentralized learning, in the context of wireless networks. So let's talk about federated learning first. So the basic architecture of federated learning is described here. The idea is to enable end user devices to do machine learning without centralizing their data. Some key features of this are on-device data sets, that is, raw data is kept locally on the end user's devices. Training is done on those devices on a shared model. And then federated computation, that is, an edge node like an access point or base station collects the trained weights or gradient updates from end users and updates the shared model. And then the process is iterated to convergence. And then I have here a last bullet, privacy by default, which I put in quotes because this is an early claim of federated learning, was that it was privacy preserving. This has since been proved to be false, and I'll talk about that a little bit more later, but it does have the advantage that the raw data itself is kept on the end user devices. But this idea that that in itself preserves privacy is actually a fallacy, which has been disproven since the original work on federated learning was done. So some of the issues we have to address is, first of all, in a mobile network or a wireless network like an IoT network, communications to the access point needs to go through wireless channels, of course. So since the wireless medium is shared and resource constrained, only a limited number of devices can be selected in each update round. So that, that's because of the spectrum constraints. And then, of course, transmissions aren't reliable due to interference. So we have two issues here to address, and that brings up two questions. First of all, how should we schedule devices to update trained weights? That's to deal with the limited resources. And secondly, how does interference affect the training? That is, how does the lack of reliability of the wireless channel affect the training? So we can look at the first issue by looking at some standard scheduling mechanisms. And I'm going to look at these three. One is random scheduling, where the aggregator or access point uniformly selects N out of K end user devices at random. So K is the total number of end user devices serviced by the access point, and N is the number of channel resources that we have to allocate. That is, say, spectral bands or slots in the spectrum. Round robin, where we just divide the end user devices up into groups where there are G of them, K over N, and sequentially select each group as we iterate through the updating algorithm. And finally, proportional fair, where we select N out of the K end user devices that have the strongest signal to noise ratios. Okay, so these are standard scheduling mechanisms, and we want to see how they perform in this setting. So the work I'm going to talk about now is work you see here, which appeared in the Transactions on Communications earlier this year. Okay, so here's what we want to look at. So the trained updates can be successfully received at the aggregator or access point if and only if, first of all, the end user is selected by the access point for updating, and secondly, the received SINR has to exceed a decoding threshold. This is bringing the wireless channel into the mix, and we'll just say that threshold is theta, so that's a parameter of the system, and we're going to compare scheduling mechanisms or protocols using the metric of the number of communication rounds required to reach an epsilon accurate solution. So what does that mean? So the problem we're going to look at here is optimization of a strongly convex function. And in that situation, we know we have a solution when the primal and dual solutions are the same. So an epsilon accurate solution is one where the difference between the primal and dual solutions is within epsilon. Okay, so that's what we mean by an epsilon accurate solution. And for these three scheduling mechanisms, we can get lower bounds on the number of communication rounds needed to achieve an epsilon accurate solution. And those are shown here. They depend on certain parameters. Theta, if you remember, is the parameter of the lower bound on the SINR that we need to achieve decoding at the access point. Alpha is the path loss exponent. This is a wireless channel. Beta, we just abstract the precision level at the end user devices of learning into this parameter beta. And N is the total number of exemplars or learning samples that are distributed over the wireless end user devices. So these are lower bounds. There's this parameter nu there. You see in the denominator of these. This is just an integral function that depends only on theta and alpha, so I haven't listed it here. These are not very meaningful as they are, but if we look at a specific example, we can see a bit more about this. So here's an example where we look at the relative values of these numbers versus the ratio G equal K over N. So we see normalized communication rounds, and we have two cases here. One is when we have a high SINR threshold, that is theta's high. So that means we need a large SINR for correct decoding. So this is a poor channel. And on the right, we need a low SINR for correct decoding. So this is a strong link, I should say. So if you look on the left, you see that the round robin and random scheduling don't work nearly as well as the proportional fair, where we're choosing based on SNR. And this is because this is a case where the channel is very sensitive to the noise level and so forth. So that's intuitively what you would expect. On the right, you see a different picture where random scheduling and proportional fair don't do as well as round robin. And this is because basically the wireless channel is quite good here. The link, if you will, is good, including coding and so forth. And so we don't really care that much about the received SINR. And round robin, which just goes through and gives everybody a chance to update, performs the best. So these are just lower bounds, but we can also, and I don't have time today to talk about them, but we've also done simulations with real data and shown that these ordering is more or less held up in real simulations with real data. So the simulations are not the data, the simulations are for the wireless channel, of course. So here's just a simple example where we use the MNIST data set, which, as you likely know, is handwritten digit recognition data set. And here we fit a support vector machine with 10,000 sample points distributed on 100 devices. So that's K, and N is 20 here. And you can see that this just compares random scheduling and round robin. This is a case of low theta. I didn't write that here, but it's a case of low theta. On the left, you can see the loss, which in this case is mean squared error. And on the right, you can see accuracy, which is the percent correct. And you can see that just as with the lower bounds, the round robin outperforms random scheduling, which we showed in that case on the previous slide. So so first of all, the conclusion is that the scheduling protocol matters in terms of the performance of federated learning and wireless network. So we might ask the question whether we can optimize scheduling, and the answer is yes. You never ask a question in a talk unless you have the answer. And one way to do that is to introduce a design metric on age, so-called age of information, which many of you may know is has been widely studied as a way of assessing the performance of IoT networks and other sensor networks. So the idea here is that in addition to fidelity of a message being received, we're also interested in the timeliness of that message, and age of information is a measure of that. So here, in this context, for an end user device I, the age of information is incremented in this way. So during each communication round, if selected, the age of information for UEI drops to 0. Otherwise, the age of information increases by 1, so it just increments. So we can write that as a little recursion. The age t at the ith device at time little t plus 1 is the previous age plus 1 times an indicator of whether the device was selected or not. So SI of t is 1 if the device was selected, so the age drops to 0, and otherwise it increments by 1. And this is what I'm talking about now. The thing I'm talking about now appeared in an ICAST paper earlier this year as well. So here's some numerical results. This again is fitting a support vector machine on MNIST data, 10,000 samples, the same problem as before, 100 devices where we can select 20 at a time. We're looking now at wireless round robin versus maximum pack. So wireless round robin is what I just described, minimizing the average age. I don't think I put an algorithm here, but basically there's an algorithm, I should say, where we minimize the average age within some constraints. That algorithm is polynomial time, so it can be run on each round. That's what shown here is blue. We call it wireless round robin. Maximum pack is another algorithm which packs in the maximum number of updating terminals at a time. Here, there's a distinction here between what we did before in that we allow individual terminals to use more than one channel resource block in this situation. So maximum pack does not allow that, whereas wireless round robin does. So you can see same thing, loss on the left, accuracy on the right. This optimizing over age is a clear win. So that shows us that we can do a scheduling protocol to optimize federated learning over wireless networks. All right, well, I'm mindful of the time, so I'm going to switch gears now and talk about decentralized learning, where we get rid of the access point, and now the learning is done in a peer-to-peer fashion. Okay, and all communication is in peer-to-peer fashion with end user devices. So I'll start by describing a general model for distributed learning within which all of these models I'm talking about apply. And it's useful here to talk about decentralized learning in particular. So we can look at a learning model where we have training examples. So these are exemplars. So you see X and Y's. So what we're usually trying to learn a mapping between inputs and outputs. So X's and Y's are inputs and outputs, respectively, of some function that we don't know. And we're trying to learn it from a set of those training examples. That's basically describes a lot of machine learning problems. So we have a training database and we have N training examples, okay? And this is similar to what we showed in the previous case. And then we have learning agents, of which there are M. So these could be smart sensors, these could be end user devices, it could be the cloud. And those learning agents, each of them has access to certain elements of the training database. So each has access to a certain number of training exemplars. And that's described by this bipartite graph where the edges, so the nodes in one part are the learning agents, the nodes in the other part are the training examples, and the edges designate that a given learning agent has access to a given training datum. Okay, so special cases of this are centralized learning. So classical or standard machine learning where there's only one learning agent and it's connected to all the data. Federated learning would be another example. Decentralized learning is an example where the number of learning agents equals the size of the training database. So each learning agent has its own training datum, and then there are connections among them based on various topological considerations. In a wireless network, that would mean those agents which are within radio range of one another would have an edge drawn between them. Okay, so I'm going to look at that case now to talk about decentralized learning. So one example of how you might do learning in such a situation is to use local learning. That is, each learning agent uses its training data to fit a model, and that's basically using standard machine learning techniques. So one of the problems with local learning, well-known problem, is that it's locally incoherent. And what that means here is if two learning agents share the same training datum, they may not necessarily learn the same target from that training datum. That is, we're trying to match a function, learn a function from X to Y. Those functions, we'll call them Fs. And if F1 and Fm are two functions learned based on, at least in part, one training datum, X1, Y1, but they may not get the same answer when applying their functions to X1. So this is called local incoherence, and it's provably non-optimal in these circumstances. Okay, so what can we do about this? We want to keep the bipartite graph structure because that's the topology of our network, but how can we get rid of this problem of local incoherence? Well, one way to do that is to go to an algorithm of this type. And here I'm talking about work that was done in 2009, before a lot of the current work on federated learning or machine learning in general, with one of former PhD student Joel Pred and my colleague Sanj Kulkarni. And this algorithm is a collaborative algorithm of the following sort. So we still have the learning agents. We still have the training database, and each learning agent has certain connection to certain training data. And the algorithm performs as follows. So we start with learning agent 1. It learns its function, and it's using a machine learning algorithm. And then instead of just moving on to learning agent 2, learning agent 1 passes its target estimates down into the database. So Y1, in this case, Y1, Y2, and Y6 are overwritten by learning agent 1's learned function evaluated at X1, X2, and X6. And then we go to learning agent 2. So it's learning something from learning agent 1 based on this connection. see it's connected to X2, Y2, so it has that in common. And so it learns, it passes its learned targets down into the database and so forth. And we iterate around through all the learning agents, and we continue to iterate until we converge. And you can show using the method of successive relaxation, successive projections, that this converges to a coherent relaxation of the global solution. And that relaxation is a relaxation of the globally optimum solution, in this case, least squares, if you had all the data in one place. So standard machine learning, it's a relaxation of that to this graph structure. So it's basically optimal within this graph structure. We get away with the incoherence problem, and we're able to, without getting rid of the local communication structure. So here's an example. This is a situation where we have 50 sensors uniformly placed along the line between -1 and 1. Each sensor observes a function of its location plus Gaussian noise. We're trying to learn the function f. That's the goal. In this case, it's linear. And we're going to do kernel regression with a linear kernel. So it's kind of an easy problem, but we can do harder problems too, get similar results. And we build a topology by letting two sensors be neighbors in the topology that is connected in the bipartite graph if they're within a radius r of one another. Okay. So what's shown on the right here is the test error versus that radius r. So as we let the connectivity grow, r goes to the right on the horizontal axis. And we're showing three cases. One is centralized, which is, you can hardly see it. It's a solid line down at the bottom. Then we have the non-coherent case of local learning up in the dotted line at the top. And you can see that the neighborhoods have to be quite large before local learning pays off. And then we have what's called SN train here, which is this collaborative learning method of Joel Pred's that I showed you. And you can, in the other dotted dashed curve, and you can see that with just a radius of 0.2, it achieves the performance of centralized learning. So the message here is that collaborative learning for fully decentralized networks is a win. I want to wrap up soon. As Reinhardt said, I have to go at the hour, but I want to also talk a little bit about reinforcement learning, just decentralized reinforcement learning, where of course, reinforcement learning, you're not trying to necessarily minimize a function, you're trying to find optimum decision or control variables, okay, without knowing a model. So it's used for Markov control problems, right? So a particular type of reinforcement learning is Q-learning, where you're trying to update the Q function, which is the payoff, iteratively, trying to converge to an optimum. Now, in centralized Q-learning, typically you use gradient updates. That's how you do that. But in a distributed setting where you have doing decentralized learning, you can't compute the global gradient because you don't have all the data. So if we have a distributed setting, like the one I've just described, we can in fact update the Q function locally, or at least a local estimate of the Q function, using a combination of gradient update of our local neighborhood gradient and a consensus type update, consensus among neighbors update. Okay, so if we combine those two updates, which we don't need in the centralized case, it turns out we can get, with some conditions on connectivity and so forth, convergence to global values of the Q function. Okay, and this is also in a paper that's a bit older with Shomo Carr, one of my former postdocs, Jose Mura. They're now both, of course, they're both at Carnegie Mellon, appeared in the Transactions on Signal Processing in 2013. And just to show you examples, here we go. This is a very simple example where we have binary states and actions. We have 40 agents, and we build a network or this graph by using two nearest neighbor connectivity. On the left, we show a typical agents, how the centralized and distributed Q values converge to one another. And on the right, we choose 10 agents out of the 40 and just show how they're converging to the Q values are converging to a consensus. Okay, so basically, with a decentralized model, using this kind of update, using both gradient and consensus, we can get global behavior out of the model in this type of learning. Okay, well, I'm about out of time, so I want to wrap up. First of all, the basic message is, in addition to using machine learning to optimize wireless networks, we can use wireless networks as platforms for machine learning. And this has applications in a variety of fields, IoT networks, autonomous driving, healthcare networks, and so forth. I talked about two kinds of such networks: federated learning, where the edge devices interact with end user devices to learn a common model iteratively, and decentralized learning, where end user devices interact with one another to collaboratively learn a model, or actions in the last case I talked about. I want to wrap up with some research issues for people to think about. First of all, I didn't really talk much about the limited resources on the end user devices. We talked about the limited spectrum, but of course, at the end user devices, there are limited resources. These are cell phones or even IoT devices where the resources are very limited. So energy, storage, computational power, and so forth. So there are a lot of trade-offs between the number of layers, number of neurons per layer in neural networks, how much energy can be expended, accuracy that we want to demand, and so forth. How big of a model do we need to train, and how much energy and computing power do we have to train them? Also, communication efficiency. I didn't really talk much about this, but there's a common model and there's correlations among data. So this is a classic in trying to upload the models. It's a classic distributed source coding problem. And so it's possible to get greater efficiencies by using distributed source coding techniques for uploading models. So that's a very interesting problem, which is currently under study as well. Another issue is that, this is not a big data problem. Usually at the edge, at the very edge, that is the end user devices, the local data is going to be fairly sparse. We're not going to have big data there. So the training sets are going to be small. So this is in the regime of a different regime from the big data regime. So incorporating domain and physics knowledge at that level is important. So things like deep unfolding and other techniques like that are useful to make the machine learning more efficient in the end user devices. And finally, I'm going to return to privacy, security and privacy. First of all, in any distributed setting, you've got to worry about malicious end user devices, adversarial training examples, and so forth. And this is a problem that we're working on here at Princeton. Also, information can leak through the gradients or model parameters. That is, I mentioned in quotes that we get privacy by default in federated learning, but we don't really, because you can show that there's a mutual information between the data and the gradient or the model parameters, so that there's not really privacy by default. And so privacy has to be actually built into these algorithms if you want privacy as one of your goals. So with that, I'm just about out of time, and I'm going to thank you and wrap up. And I don't know, Reinhard, if there's time for questions or not, but I do need to go at the top of the hour.
I have one question, Vince. Suppose you were a beginning graduate student. Which research area would you pick for a PhD thesis?
Yes, I think to be honest with you, I think I would like to work on this privacy problem. There's already been some work in that area, but I think it's far from solved. Or if I didn't work on that, I think I would work on this problem of incorporating physics knowledge and domain knowledge. And in fact, the PhD thesis that I'm going to be examining at 9 o'clock is exactly on that topic. So people are working on it, and I'm about to go listen to a thesis about that. So,
all right, great talk. Thanks a lot, Vincent. Thanks a lot for that.
Sorry, I have to go. I hope you enjoy the rest of the
Yes.
Thank you. Bye-bye.
Thank you, Vincent. Yeah, thanks a lot.
Thank you.
Okay, all righty. We are coming now to the presentations of our winning teams. So the judges had a really tough time picking the winners. And originally we decided that we would have a first prize, a second prize, a third prize, and then 3 runners-up. But we decided to increase the number of winning teams to 10. We are going to increase the prize pot by a little bit. So what we are doing now in this session is of the top 10 teams that made it, each of you will be giving a presentation of 2 minutes. 2 minutes, we said originally 3. I'm cutting this down to 2 minutes. So it's like a 2-minute elevator pitch that a startup has to do. So all the teams have prepared 2 slides. There's a title slide, and then there is 1 slide where they explain their work. So you don't have to be afraid. All of you are already winners. And I'm just reading out the order in which we'll go. And I hope that everyone is connected. So we'll start with the first 5 teams are Weenie Wit, then Imperial IPC1, then Salzburg Research, then UT Nakao Lab AI, and the Beam Zoop. And in the second half, we have Atari, then Linkbusters, then AI Maglev, then No Boundaries, and AI IEC Research. The order is random and doesn't implicate who is first or who is second. So, and we would actually ask you to share your screen because we haven't been able to put everything into one master presentation. I have a bell here, which is, I don't know whether it's a Swiss cowbell or a Swiss jingle bell. So after 2 minutes, I'm going to ring the bell and then you please stop. Yeah, no worries. You are all winners. You don't have to be nervous. Okay, so we start with Weenie Wit, with the team Weenie Wit. Are you ready?
Yes, I'm here.
Okay, go ahead.
Here? Yes, okay, thank you. Okay.
Can you share? We don't see it yet. Oops, my bell. Okay.
Okay.
Go.
Respected judges, ladies and gentlemen, good morning, good afternoon, and good evening.
Oh.
We are Weenie Wit from China. It's
Weenie
our
Wit,
great honor that
we don't see your slide yet. Okay, now we see it. Now we see it. Yeah. Okay, good. Yeah. Continue.
Okay. Yes, it's great honor that we can have another 2 minutes here to share our ideas. And first of all, I'd like to introduce my team and team members here. They are Han Zhengfu, Wang Zhiguo, Zhang Yiwei, Wu Desheng, and Li Sicong. In this challenge, we need to address a problem that can commonly seen today. You know that the existing network topology planning does not fully consider the increasing network traffic and uneven network link computation utilization, resulting in difficult topology optimization and increasing investments in network construction. And by using AI technologies, we can solve this problem. And our solution consists of 2 parts. The first part is traffic forecast, and the second part is topology optimization.
1 minute left.
And okay, we actually set up a complete network topology analysis and optimization system. And we further optimize the recovery network topology by adjusting the links with unbalanced load, while 3 different ways, including link combination, partial link optimization, and optimization by node transfer. With outstanding performance, we ranked #1 in both preliminary contests and finals in China. The original topology is part of practical network, and our standing performance prove that our solution features good model generalization and is worth promoting. Thank you so much.
Wow, okay, thank you. All right, next team is Imperial IPC1. So while you're getting ready, let me just also say that some of the judges thought that some of the presentations that for one reason or the other didn't make it to the cut, but they presented really innovative work. They would also feel comfortable if they get an award. So we're also going to hand out honorable mentions, and we'll notify you about that in the coming days. Okay, so team number 2 is Imperial IPC. I'm going to start.
Yes, hello. You should
now
be able to see me and give me yeah, do you want to continue? Share screen, sure, yeah. Can you see my screen?
Yes, okay.
All right, so I'll start now. Hello, everyone. My name is Mikołaj Jankowski, and I'm a PhD student at Imperial College London. This is my great pleasure to give you a very brief introduction to our solution to the beam selection task. This task is very challenging and important, especially in the 60 GHz regime we considered, due to the very pointy beams. This topic is widely explored by research community as well as in ongoing standards. In our work, we aimed at designing a neural network capable of finding the best beam pair to reduce the significant overhead of the exhaustive search. We used the RAMOptime dataset of simultaneous LiDAR, location, and image data. In our work, we only use LiDAR and location data as we found this the most effective site information. Our point cloud preprocessing aims at obtaining quantized top view of the scene and allows for reducing the complexity of the input by the factor of thousands. The top view representation is used as an input to our convolutional network that was carefully designed to require minimum number of parameters while achieving the satisfactory performance. It allows for a 55 times reduction in the number of parameters, 100 reduction in the number of flops compared to the baseline. At the same time, our network achieves 7% better top 10 beam selection accuracy. To allow for even greater reduction in the number of parameters, we decided to apply pruning, which is a method for removing the redundancy within the neural networks. With a simple magnitude-based pruning, we were able to reduce further 50% of the parameters from our network, sacrificing less than 1% of the final accuracy. Creating such a lightweight network enabled us to use the federated learning approach, which allows for a distributed training during normal operation of the system. Federated learning scenario considers collaborative learning where each user gathers its own data, performs local iterations of the training, and sends the network update to the base station. This strategy enables us to reduce the communication load, as we don't have to transmit dense point cloud, but only the parameters of the network. We have shown that our network can be successfully trained with this communication efficient distributed training and achieve satisfactory performance. Thank you for your attention.
Wow, great. Thanks a lot. Sticking to the time, Imperial IPC1. We come to Salzburg Research. Salzburg Research, are you ready?
Yes.
Okay, please share your screen and go ahead.
See the screen?
Yes, we can. Please go ahead.
Thank you. My name is Martin Happ from Salzburg Research and IDLab Salzburg. And in the context of the Graph Neural Network Challenge, it was asked to predict the mean per packet delay for different networks. So the networks can vary in terms of the topology, in terms of the network configuration, like routing and queue scheduling. So for a bit simpler problem without queue scheduling, there's already a published solution, which is called RouteNet, which was developed by the hosts of the challenge. And we could either modify this RouteNet or develop a completely new approach. And we decided to modify the RouteNet. So here's a picture of this RouteNet model. Gray is the original, and our modifications are in green. And so our team is an interdisciplinary team. So there are people from computer sciences, people from mathematics and statistics. So some of our changes were really motivated from a network point of view, which is basically the preprocessing of the input variables. So this RouteNet model is based on something called message passing, which is basically this sending information from path state to link state and back again. And we had to preprocess it such that node information can fit into this scheme. Another thing that we have done is optimize with respect to hyperparameters, which was very important. So hyperparameters, for example, the dimension of hidden states for path information and link information. So overall, this training took about 48 hours on a single GPU, and after the challenge has ended, we have also a bit improved it even more. So the error over error rate, you could reduce it even more, and also the training, you could reduce it a bit. Thank you for your attention.
Wow, great. Thank you. Also sticking to the time. You've been doing this, I guess, all of you more than once already. Okay, we're coming to Nakao Lab. Are you ready?
Okay, I will share my screen.
Okay. Let's see how that works. Okay, coming up and ready. Yep, go full screen mode and then yeah. Lower bottom, right? Yes, exactly. Okay.
Okay.
Good.
Hello, everybody. My name is Fei. My team is UT Nakao Lab AI from the University of Tokyo. Our topic is Summer 1 from KDDI, analysis of root information failure in IP core networks by NFV-based test environment. The COVID-19 pandemic has forced a global and large-scale stay-at-home and online meeting in many countries. The increasing traffic has introduced more network and device failures than before. For example, the news reported Google losing an estimated $1.7 million in ad revenues during their outage on November 14, 2020. So it's very important that how to automatically and rapidly detect network and device failures. Unlike other solutions that use novel but unreliable process, we prefer to employ a high performance, practical, and reliable approach to solve real-world problems. So far, our solutions performance is the best one in this KDDI term in terms of accuracy and speed. We have open source all of our works, and the detailed report would be found at GitHub. Thank you. That's all.
All right, excellent. Thanks very much to Japan. And we move to Beam Soup. So Beam Soup, I think you should get an extra award for the name of your team. Okay, go ahead. Yes, we see everything. Go ahead, please.
Hi, everyone. I'm Matteo Zecchin, a PhD student from the Communication System Department of Eurocom under the supervision of Professor David Gesbert and Marius Contouris. And this is my solution for the millimeter wave beam selection problem. So we know that one of the main challenges in 5G networking is efficient antenna reconfiguration, and a particular tough instance of this problem is the millimeter wave beam selection. This is due to the fact that due to high channel variability, this kind of procedure introduces a high overhead in communication. On the upside, in this particular scenario, there is the potential benefit of leveraging high dimensional data, such as images or LiDAR sensors. And therefore, the question that we pose is the following: can we extract useful patterns from this high dimensional sensory data and produce good side information to be exploited during the beam alignment procedure? The answer is yes, we can. In fact, we provide a machine learning model that combines different data modalities to predict the quality of the communication beams. This solution has outstanding performance. In fact, with only a 10-step search, so a minimal overhead, our model produces the best beam 92% of the times, whereas a random search in the same setting would require to sweep through 235. It also proves that combining different sensory information is good. Indeed, our model reduced by 30% the overhead by doing this. Finally, our model is trained using a loss function that is inspired by knowledge distillation techniques. This has dual benefit. It not only gives this outstanding performance, but it provides model with very informative outputs. With that, I mean that our model not only gets the best beam, but it provides full guesses about the whole spectrum of beams, meaning that if we fail to predict the best one, we still have information about the weaker one that can be still used as backup information for the beam selection phase. That's all. Thank you for the attention.
Fantastic. You're all doing a great job. Fantastic. Thank you. We have the first half, and now we are moving to the second half. That is Atari. Then we have Link Busters. We have AI Maglev. We have No Boundaries. And then we have IEC Research. And Next, so is Atari, please.
Yeah, thank you. I'll try to share the screen, so tell me if you see it, please.
Yes, perfect, perfect. If you go full screen, yep, perfect.
So, okay, so hello everyone, I'm Paula Soto, leader of Team Atari and PhD student of Universitat Antwerpen and Universidad Antioquia. And this is our solution, a graph neural network approach for throughput prediction in next generation VLANs. So in the problem statement that we were participating, we were asked to predict the aggregated throughput in highly dense scenario with VLANs that use channel bonding. So channel bonding is a technique proposed for Wi-Fi that increases the channel capacity by bonding 2 or more adjacent channels. In that way, Wi-Fi can deliver a higher throughput per user. However, channel bonding also imposes some challenges in highly dense scenarios, as the interference caused by different stations and neighboring VLANs is increased. Our proposal for this challenge is a graph neural network that, given that the deep learning approaches do not exploit the information carried in the graph-like structure, and we define a graph as a set of nodes and a set of wireless links, and each has its own set of features. So for instance, features such as localization, configuration are related to the nodes, while the features like distance and interference are more related to wireless links. So we believe that the key for obtaining good results was the simplicity and naturality of the solution to exploit the problem structure. And the concepts that of the graph neural networks can be easily mapped to networking problems. So that's it.
Great, thanks a lot for that one. And we are moving to, who is displaying now? Yep, please, please go ahead. Yes, thank you. Good. Who is presenting? Takanori? We don't hear.
Okay.
Okay, now we
am I audible now?
Yes, that's
Okay.
fine.
So,
yeah, that's fine. Yeah, okay, we see that.
Okay. My name is Dheeraj Kodgiri. I'm a researcher at NEC Corporation, Japan. I would be presenting a brief overview of a submission to problem statement 36, which was radio link failure prediction. So reliable wireless backhaul links are essential component of 5G networks. However, these radio links typically use millimeter wave, which are susceptible to bad weather conditions. Our goal in this work was to predict radio link failures for next 5 days, given weather forecast made today. As part of the challenge, we were provided real-world data from more than 1,000 radio links, 100 weather forecasting stations, spread across the entire country of Turkey for an entire year of 2019. Apart from the fact that we want to predict failure based on weather forecast, which itself is a prediction, what makes this problem particularly challenging is that radio link failures are very rare in real world. Less than 0.5% of the data had any kind of radio link failures to begin with. Our biggest takeaway was when it comes to real world data and rare event detection, we cannot rely on machine learning models or AI models alone to solve it. We had to augment it with a lot of data pre-processing, leveraging on conventional knowledge on radios and wireless communication networks. This enabled us to generate meaningful features, which can then be used by relatively simple random forest-based model to predict link failures. In our approach, apart from considering weather forecast and radio link configuration, we developed a graph-based method to account for spatial and temporal correlations between the radio link performance and weather station forecasts. We also took wind flow patterns into account, and we even took topographical features of surroundings into account. After all, radio link behaves very differently in open land than in a dense urban area. With our approach, we were able to predict radio link failures fairly reliably. Not only prediction failures, but also we had an associated confidence level with the predictions. And the predictions were interpretable. That means that we can look at the suspected major cause for the radio link failure. All these things make the approach practical in real world. And all these things were accomplished with low computational complexity. Thank you.
Great job. I don't need to use my Christmas bell. So we go next. This was link. Now we come to AI maglev, and I think my colleague Thomas is sharing that. Okay, so next team, please. We don't hear you. My colleagues are sharing the screen. Yue Wang, we don't hear you, or I don't hear you. Okay, I heard someone saying, "Ah, was that Yue Wang? Was that you?" All right. No, we don't hear you. Let's take the next one. Let's take no boundaries, and then we come back to you. Maybe you can fix that. All right, team no boundaries. Are you ready?
Yes, we are ready.
Okay, please share.
Can you see my screen?
Yes, we see that. If you go full screen.
Okay. Hello, everyone. We are No Boundaries team. Our title is Applying Machine Learning in Network Topology Optimization. Nowadays, telecommunication has become an indispensable part of our life, assuming that the telecommunication system is a human body. Transmission is as important as vessel system, while most of the vessels are not healthy. Some of them are overloaded. Meanwhile, the others still have a lot of capacity. It not only affects the customer experience, but also affects the development of communication services because of the resource problem. We proposed our own solution. In this page, we'll introduce result of the test in Cali City. We can see that the AI optimization solution restores 16 overloaded links to a normal load, save a lot of money and human resources, and also hugely improve traffic absorption capacity. So I think our solution is good at solving this kind of problem. We believe that our solution are positive in 3 aspects. Firstly, 5G technology can bring better network speed, help the AR and VR industry, and connect everything. It will deeply change our society, and it also brings more complexity. We can use AI technology to reduce costs of operations and maintenance, also save much energy for a better Earth. Secondly, in China, mobile developers, platforms, and standards form an intelligent operation and maintenance ecosystem to support China Mobile's rapid, large-scale 5G construction and production, which achieved efficient operation and maintenance of complex networks. Finally, most of the current AI development is the 2C mode that focuses on serving users based on users' needs and conforms to users' living habits. This is an exploration of the 2B model of AI development serving the telecom industry based on the ITU specifications, which provide an example of AI 2B model. Thanks a lot. That's all.
Great. Thank you very much. This was No Boundaries. Let's go to IAC research, and then we come back to the last one, AI maglev, IAC research. Go ahead, please.
Yes. Okay.
Okay. Yeah, we can see it. Go ahead.
Thank you very much.
Yeah.
Thank you. Good morning. My name is Juan Samuel Perez, and I'm the team leader of IEC Research. And we worked on the radio link failure prediction using weather information, which is the problem statement number 36 of the challenge. And the problem statement says like this: given the region-wise historical data sets derived from Turkcell's networks with weather forecast as well as radio link performance for a given frequency band, predict the line of sight radio link failure occurrences, right? So radio link failure prediction can result in mitigated downtime or reduced service degradation to the subscribers. For our proposed solution, we formulated and trained a decision tree-based model that features a simplicity in the data pre-processing stage. It gave us highly interpretable predictions and used a very reduced amount of features, 29 in total. And this was from an original data set with a highly dimensional input feature space. And our model then produces actionable information for a network operator that allows them to see in advance, right, the occurrence or forecast in advance the occurrence of these radio link features. Our model relies heavily on the weather forecast data and performs with a total accuracy of about 90% and a rate of 90% and 60% recall for the false true classes. And this was very relevant because we trained over a highly imbalanced data set where the true class was less than 1% of the total data. Our model then finds that the most important features were forecasts of thunderstorms and rain, the height of the RF site, and the historical data concerning the link unavailability. Thank you very much.
Okay, great. Thanks a lot. Okay, so we're trying to fix the issue with AI maglev, but AI maglev, you don't need to worry. It doesn't affect the final result. We'll take you afterwards. We are moving to the award ceremony. Our Secretary General is here, and he has a sharp deadline at in 4 minutes. So, Hulin, we're showing the certificates, and if you just read out the certificates, we are starting. Actually, yeah. Can you?
Yeah, I can see that one.
Yeah, that's not the. You yes. Wait. We do this afterwards. We're doing the award ceremony.
I'm so sorry. I'm so sorry. There's something wrong with my network. Yeah. Sorry.
You wait. We do you afterwards. We do you afterwards. Okay. We do you after like in 5 minutes. Okay, good. It doesn't affect your score. Don't worry. Can you unshare, please?
Okay.
Unshare. Okay. Now don't worry. It doesn't affect anything. If you go off screen, if you turn off the.
Can you see my screen? Okay.
You wait. We will take you later. We will take you in 10 minutes. Yeah, we will take you in 10 minutes. If you just disable, well, maybe it's faster just to take you, but okay, good. Can you unshare? Can you unshare?
Yes, Chair. Can you see my screen? Yes.
Do not share. Wait, we'll take you in 10 minutes. Don't worry. We'll take you in 10 minutes. You're part of the award ceremony, yeah? Okay, Hulin, we're swinging this in real time.
Thank you. Yeah. Because I already opened my access to United Nations headquarters meetings now, so my platform opened there, so I cannot stay here too long. Because Secretary General of the United Nations will be showing
up very soon. Go ahead. So you just, Gino, a little bit louder the music. Okay, we have music, but all right, let's.
I cannot hear music, but you asked me to read the certificate?
Okay, Gino, next, let's go to the awards.
No music come.
Okay. All right, good, we heard that. Okay, Gino, we come to the, I'm not sure what's coming now. Okay.
So. That is ITU AI ML in 5G Challenge Encouragement Award now. NET, Intel, UC3M, Netcom, Hideki.
Yes, good.
Good. Congratulations.
Okay, next one. There are quite a few, Hulin. There are quite a few. Yeah. All right, next one.
Yeah. Okay, next one. ITU AI ML in 5G Challenge Honorable Mention Certificate will be
Gino, that was too fast.
Will be station 1, no boundary. What it means?
Okay, okay, we stay with that one.
Yeah, Honorable Mention Certificate. Yes, that is Stereotech, Diagnostics. USR2 or USR2, Henoko King. Very good.
Next one, Gino.
That. What do you mean that? What do you mean this one?
Just
this,
public poll. We did a public poll, so these are the winners.
So that one is the public poll winners. Session 1, no boundaries. Session 2, Imperial IPC 1. Session 3, air diagnostics. Session 4, learned Chester.
Okay, thank you. Good. Next one. All right, now we come to the top 10. Gino, are you getting ready? Yes. Okay, now can we read that? Okay, so these are 4 fourth prizes. Can you read that?
Yeah.
I'm not sure whether it shows up big
A
enough.
little bit small. That is the first one. No.
Yeah.
It's IEC research.
Good.
Intec University. Dominican Republic.
Okay. Next one.
For the
yeah.
Yeah, you should put that a little bit bigger. You know that I need AI assistance. I'm aged people.
Yeah, but you read it well. You read it well, Hulin.
So that is one, and then we have another one. This is the beam soup.
Yes.
Eurocom France.
Yeah.
Right.
Yeah.
And then we have another one. ETA, the University of Antwerp, Belgium, and Universidad de Antioquia, Colombia.
Yeah.
And the last one on the screen is Link Booster.
Yeah.
NEC Corporation.
Okay, great. Thank you. And now we come to the third prize. The writing will be bigger now.
So I'm going to join the United Nations conference for disabled people. I'm disabled. You know, I'm aged people. Glasses to read the text.
It'll be done in 1 minute. Okay, so.
See, I will be proud to tell them that TSP has developed a lot of standards to assist people with disability. I'm one of them.
So that's third prize.
Third prize. So that will be Imperial IPC 1. So Imperial College London, UK.
Yes.
And then UT
Macau Lab.
We have your name here covered my screen. Why I have Reinhard Shaw here? You know that is.
Well, sorry.
University of Tokyo, Japan.
Okay. Okay, that was third prize. Okay, and now we come to a second prize.
And your name is always there. You know that sounds.
Well.
Cover my part of my text.
Okay.
Okay, this is a third prize, right?
Second. Yeah. Second prize. Second prize. Second prize.
Maglev. No.
Yeah.
AI Maglev Institute of Computing Technology, Chinese Academy of Science, China.
Yes.
And another one is Salzburg Research, Austria.
Okay, that was the second prize, and now we come to the first prize.
First prize is Winnie Hit, Xiaozhi, China Mobile Shandong, China. And then no boundaries. This is China Mobile Guizhou, China. Congratulations.
Okay. Okay, thanks very much, Hulin.
Yeah, I have to leave now.
That's fine. It was perfect.
And
Thank
you
you
want
very
to
much.
have photo again?
If actually, yeah, if all the panelists, that would be great. Yeah, can all the panel, everyone who is on the panel can
because
turn
my
on?
meeting in New York is already opened.
Yes,
I
can
show
all
myself
the
there.
panelists turn on? Then we do a photo op. Okay, everyone who wishes to turn on his or her camera. Still a few missing, so who are still there? Okay, turn on your cameras. Great, thank you very much. Wow, okay.
Okay.
More, we still have more. Paulo Sato, okay. Good, all right. Okay, we take a group picture and we Photoshop it a little bit to make it really look nice. Okay, thank you very much. Thank you very much, Hulin.
Yeah, okay, thank you.
Being with us.
Bye-bye.
Okay, bye-bye.
Thank you.
All right, so this was the award ceremony. We were swinging this in real time. I guess it did work. And now we have a couple of more things. So we have 25 minutes left in the rest of the program. We'll have now a presentation of my colleague Alessia, who is managing the ITU journal. That will be 5 minutes. Then we'll have also my colleague Vishnu, who is giving an outlook into 2021. Then we'll have a couple of voices, a couple of sound bites from our participants, from our colleagues that supplied problem statements. And then Chase will be saying goodbye. Okay, Alessia, if you share, can you share that? And then 5 minutes, it's over to you.
Thank you. Thank you very much. Can you all hear me?
Yes, we can. Can you go full screen?
Yes. Can you see the old screen?
Perfect.
Okay, very good. Thank you so much. Thank you for the opportunity to present the ITU Journal and its current activities today at the Grand Challenge Finale. My name is Alessia Magliarditi. I'm the ITU Journal Coordinator. So the International Telecommunication Union has established a scholarly, peer-reviewed digital publication, which is free, fast, and for all. And it provides a complete coverage of all communications and marketing paradigms. It is free of charge for both readers and authors, and it is fast because we are determined to give detailed, constructive feedback on submitted papers in less than 3 months. Our editor-in-chief is Professor Ian Akilditz, the Ken Byers Chair Professor Emeritus in Telecommunications at Georgia Tech, USA. He's also editor-in-chief emeritus of Impact Factor Journals and has an outstanding H index, 126, and a number of citations over 121,000. We have also appointed 54 editors to handle the review process of regular papers. They are internationally recognized experts in the forefront of the telecommunication research community. And today I am very pleased to launch together with you the special issue on AI and machine learning solutions in 5G and future networks. Based on solutions and results from the ITU Challenge, the ITU Journal is calling for papers by the 22nd of February next year from hosts and participants of the ITU Challenge to submit their solutions for publication in this special issue. The complete list of tracks and topics is available at the ITU Journal webpage, and also the full call for papers. I'm very pleased to also announce the guest editors of this special issue. In particular, I would like to give my thanks to the leading guest editor, Dr. Qin Ling from China Mobile Research Institute, and to the guest editors that have accepted to contribute to the preparation of this special issue. Professor Nakao from University of Tokyo, Professor Clautau from the Federal University of Pará, Professor Gonzalez from North Carolina State University, and Professor Cabello Aparicio from the Barcelona Neural Network Center from the Technical University of Catalonia. So I encourage you to submit your contribution online to the EDAS platform. We are launching our inaugural issue. It will be published on Monday, next Monday, 21st. It will include 10 high-level original papers from internationally recognized researchers, and the publication will focus on areas of relevance to the work of the ITU, such as IoT, network automation, machine learning and AI, vehicular networks, infrastructure and spectrum sharing, 5G, and so on. The ITU journal publishes online all year round, welcoming papers at any time on all topics within its scope, and there's no page limit. For a complete list of topics, you can check the journal's webpage, and the submission can be done electronically, and here is the link for your proposals. And we're also preparing 4 special issues in addition to the one that I've just presented. The deadlines for the submission is between end of January and mid of February. And these special issues are on the following themes: Internet of Bio-Nanothings for health applications, Internet of Everything, terahertz communications, and wireless communication systems in beyond 5G era. If you have any idea, any proposal on a special issue, on a new special issue, please don't hesitate to submit your proposal through the online form that can be found at the journal's webpage. And also, if you're interested, you can sign up at the journal's webpage to get more information on the latest opportunities for publication in our journal. And so Free Fast for All, the ITU journal, aims to promote accessibility of ICT research to academics and industry researchers across the world. If you have any queries, if you need additional information, don't hesitate to contact us at the journal@itu.int, and you can also visit the ITU journal homepage for updates. Thank you very much for your attention, and Reiner, back to you.
Okay, thanks, Alessia, for that. So I hope that the participants will be submitting papers to this special issue. So one thing I promised you, Wei, that we would take the presentation from AI MagLab. Let's do that. And at the end, maybe we can piece everything together in a nice video. Wei, are you ready? Yeah, okay, 2 minutes. Okay, great. If you share and then I go off screen.
Can you hear me?
Yeah. Yes, perfect. Perfect. Yeah, go full screen, please.
Okay. First, I'm so sorry for my, there's something wrong with my computer.
Don't worry, just keep going.
Good morning, good afternoon, and good evening, gentlemen and judges and experts. I'm Wang Yuwei from the Institute of Computing Technology, Chinese Academy of Sciences, also from China. And my solution problem statement is DNN inference optimization coming from the comparison of deep learning models from GTE topic. And in my team, there are 4 members, including me, the Dr. Sun Sheng, and other 2 students. And our solution title is End-Age Cooperative Interface of Deep Learning Model based on DNN partition. Next, I have a overview from my solution. The first, we provide an efficient dynamic partition algorithm for DNN. The partition problem of DNN will be solved by alternating dynamic programming method. And the second, we considered something most important indexed in our solution, which is the device load change. And the third, end-to-end collaborative inference framework based on DNN partition is designed and executed. Experiment results show that our proposed DNN partition solution can adaptively adjust the pattern stitches of DNN model according to its own characteristics and running environment, and significantly reduce the end-to-end inference latency. That's all. Thank you.
Okay, thank you very much. That was AI MagLab, and congratulations also on the prize that you received. Okay, so we are coming now to a colleague that I very much appreciate, and without Vishnu, we would not have been able to run that. So the chairman of our focus group, Machine Learning in 5G, called Vishnu the champion of the focus group. And Vishnu, yeah, without you and Thomas, this baby would have not taken off. So you will be presenting your wish list for 2021. Vishnu, please.
Yeah, thank you, Reinhard. Could you confirm if you can see it?
Yes, perfect, perfect. Yeah, if you go full screen.
Okay, yeah. Okay, so yeah, my name is Vishnu. I'm an independent research consultant. This is a wish list. So basically, we are looking at outlook for next year. So if you are planning to compete or if you're planning to host, this is where you should be. And let's go straight for it. Our first wish is to have more open data. So you see here, there was this giant who has a garden and all that. You know that story, right? So this is a walled garden. We are all kind of standing outside, and the giant says that it is his data. It's somewhat similar situation here, but there is some amount of hope for the people outside. The data from the real network is all private, is actually a myth. And we always hear that it cannot be opened for the challenge, but that has been proven wrong. We have colleagues right here who have kindly given us network data from real network, and they are available in the challenge website. So there is a way to do it that has been proven in this version of the challenge. We would like to do it more. Along with, we would also enable data sharing with Geneva Sandbox, which is according to the standard that you see here, Y.3172. We'll also work with the data providers to pre-process the data. In this version of the challenge, we worked on data sharing guidelines, but we will go one step forward to make it available. We'll also work on simulators and data augmentation along with the host to make sure that quality is assured. The next wish is right here, which is basically equal access. You know, equal access for these tools is very important, and one of the things which you saw is that you know, there is a myth that AI ML challenges are all done by data scientists. Data analysis take away all the prizes. That has been proven wrong as well, because you know, there is a mix of participants here, students, professionals, researchers from about 60 countries. You saw them as part of this challenge over the last 3 days. They have been here, and many of them have been here, and they have been working over the period of the year. The wish is to give equal access to tools, because as part of our engagement, we find that some of them felt the need to have GPUs, but there are no GPUs. They don't have access, or they don't have data, or they don't have tool sets which are required for model training and testing. So this is a wish for us. How do we do it? We provide these open toolkits, which are part of ITU standards, engage with partners, provide ready to cook, I mean ready to use toolkits which are built in, and you know, especially for the students, this is really important. We also provide mentoring, roundtable sessions, and other participant engagements. We wish to continue that to next year. So basically what happens here is that there are ITU standards which are connecting different types of sandbox instances from academia, company, you know, open source, and member state sandboxes. So I'm trying to move. Yes, so this challenge is about creating an ecosystem. It's not a standalone thing. The challenge is not a standalone activity. It is we are here to create an ecosystem, right? The myth is that we are here to win some dollars or Swiss francs as prize. That's not true. I mean, if you look at the prices which we announced, it's not much. I mean, you work for 1 year to get this much. That's not exactly the value of your time, right? So you're here for something else. What is that? I mean, we also created a set of webinars. We created roundtable discussions, open source. Most of these solutions are in GitHub. Yeah, we do have the dollars on the table, but there are other things as well. That's what I'm trying to tell you. The wish is to continue this, to create a core team with the mindshare, with a distributed team, who work on AI ML in networks, identify this core team and work together for future challenges. You see on the right side, the challenge does not stand alone anymore. It works with other types of events that you see here and the standards that we produce. In fact, both Secretary General as well as JSUB mentioned this in the beginning, that we should work with the standards, and we do that along with the pre-standard research which we work as well. So it is basically interconnected, as you see here. And also, this is, I wish we had more time. It is, I mean, we have 24 hours, but we wish for one additional hour or so, because there is a bunch of activities which we do here. You see here, step 1, we call for regional hosts, we identify problem statements, we identify data, blah, 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 blah. This is actually done by us. Our colleague Thomas, he's almost a Superman. So we did this over the period of the year, right? So this is actually quite a bit of work. We want to start this early. So the outline for next year is that we start the planning early. You will hear from us to do this. Increase the automation with this sandbox that I told you and so on. Provide enough time for analysis and solution approaches. This again is coming back from the feedback from the teams that they could have done more if they had more time. So that's what is happening here. And then you know, we would like to focus more. The training phase is over. Now it is evaluation testing phase of this model. In this model, we would like to get it bigger. With multiple owners, with you know, collaborative problem statements. We would like to get it better. We would like to separate out students and professionals. We would like to do open source. And then we would like to also look at you know, domain versus data science problems and so on. So in this as actually Dr. E from China Mobile mentioned in her talk, open data is actually one of the biggest challenges which we face. ITU is bravely stepping into that area. Some of the example teams you see here, if your project is not here, don't worry. You can add it to the list here, and you can send us, talk to us over Slack, and we will work on it. We would like to continue discussion on AI ML mechanisms, autonomous networks, Open RAN. You know, the radio link failure which we did can be extended to do disaster, campus networks, and so on and so forth. So these are some focus areas which we would like to work on. So talk to us. If you click on this launch challenge button that you see here on your screen, nothing will happen. I'm just joking. You can't do anything with it, but we would like to, with this wish list and the focus, we would like to launch challenge 2.0 according to these outlines. With that, thank you so much, and over to you, Reinhard.
Thank you, Vishnu. Big thank you again to you and to Thomas for managing the challenge. Okay, we have a couple of sound bites from experts that helped us manage the challenge. And we have in principle a deadline on the hour. So I will have Nakao Sensei from Japan. I'm just looking at the clock here. I don't know how many calls we had. Aki, where it was midnight for you. We also have Jose Suarez Varela. We have Salih. If he is, yeah, he's here. So, Aki, would you say a few words on your impressions on the challenge? Yes, thank you.
Yes, thank you, Reinhardt. Vishnu, you got me. I just pressed the red button, nothing happened. Wait, so thank you very much. So, okay, I can tell you a little bit about our experience towards this the 5G AI ML challenge. So at first, COVID-19 pandemic misfortune discouraged our participation at first. And we all thought at first that this challenge would be called off. However, looking at all these other hosting countries pushing this hard in this adverse situation, we gradually catch up and the speed and finally keep up with the other countries' efforts. And the preparation time for us in Japan, local round was really short, but Reinhardt, Vishnu, Thomas helped us a lot. And hosting Japan, it's actually rising. It's a technical committee of Japanese Telecommunication Society. And a group of professors and researchers, we tried very hard to make arrangement for a local challenge round. And we finally got 2 problem statements from KDDI and NEC. Thank you very much for your cooperation. And each collected 20 registrations and finally 7 and 9 submissions respectively. So all of them are actually students. And I was surprised to see all the teams are formed by students. And in the course of this effort, we had 2 webinars and 2 workshops, and all supported by the IT staffs. And we also had a workshop on the prior night and to the finale, and for a student practice talk. It was quite a successful in my opinion, and in the end, 6 selected teams made it to the final conference and presented, and their results, and I really appreciated that. Reinhardt, Vishnu, Thomas, Alessia, thank you very much for making this challenge happen. And we really appreciate that. And all the judge panels, and finally, thanks to our rising community, the Japanese government supported also TTC, 5GMF, NEC, KDDI, all of them supported. And we will do another round next year. Thank you very much. Yeah. That's all from me.
Okay, great. Thanks very much, Aki. And again, thank you for staying up until midnight again. And we hope we can reduce these midnight calls next year for you. Okay, we have Jose, are you there? You want to say a few words? Yes. If you also keep it to maybe like 1 or 2 minutes or so, your impressions.
Okay, hello all. So this is Jose Suarez Varela from the Barcelona Neural Networking Center. And I'm part of the organizing team of the Graph Neural Networking problem statement. So first of all, I would like to especially thank Thomas, Vishnu, and Reinhardt that they pushed this great initiative from the beginning. So thank you for your great effort to convert it into the first worldwide competition on network AI, which has been very important for all of us, I think. So also many thanks to the other problem hosts for raising a great variety of real-world use cases. So I think that nowadays one main barrier that we have in AI for networking is the lack of public data sets. So I think that it was an excellent opportunity to gather data publicly available that can serve as a reference for benchmarking future research in network AI. Last but not least, many thanks also to all the participants that made all this possible. So I would like to remark that we have seen these days very talented, motivated teams in the presentations. that have proposed solutions even beyond the state of the art, which has been really impressive, at least for me. So overall, I think that this has been a good opportunity to encourage the application of AI in networks and also to promote these kind of solutions into standardization activities. And I would like to say that it has been a pleasure for us to host a competition here. And now that also we know that one thing of our problem statement has been awarded, I feel even happier to have participated here. So final remark, I think that to address the challenges of next generation networks, we need more experts in networking with education in AI. And that's why I think this initiative will have a large impact, not only nowadays, but also in the long term, as it can help attract students and young researchers and professionals to the field of AI for networks. So after all this, I'm looking forward to seeing a new edition in 2021, really. So thank you very much.
Thanks very much, Jose, and for your great contribution to that. Yours was one of the favorite problem statements. Do we have Salih here? Salih, you want to say a few words?
Yes.
Okay. Yes, Salih, we hear you. You can go ahead, and then we hand over to Chesap. Salih, you want to say your impressions? Yeah.
Hello, everybody. I think I would like to first thank you, Reinhard, Vishnu, and Thomas for arranging this event. This was a long and dedicated event. We joined it a bit late in the game, and thank you again for making it possible for us to join. We had very good webinars with the participants. I think that also helped us to understand our problem better. It's a challenging problem, and with the questions, actually we provided several interactions. It was also difficult for releasing operator data. In a sense, I think this was a good start for us. We made it possible. We are still getting some questions about the data set even after the challenge. I think there are some people are interested in terms of working more on the problem. We had great submissions, and we are also happy to see those getting rewards in the end. We are looking forward to participating in the future challenges. Thanks again for the opportunity.
Thank you very much, Salih, and looking forward to having you on board next year. Okay, we are coming to the end. One thing which we didn't get to was we also have prizes, the judges' prizes, about 20 or so. There is a certificate and a cash report. We will be notifying about you about that. I'm going to hand now over to Chesap. Chesap, you have the final word.
Yes, thank you, Reinhard. I have to start with my sincere congratulations for all winners, as well as all contributors. You make us, everyone, as a really winner. Also, my sincere thanks for all sponsors and the colleagues who works to run of this event behind the scenes, and the experts and TSP staff, especially including Reinhard. 5G, IMT 2020 and ITU name, just commercialize and will continuously grow and evolve. So contributions from AI machine learning should be essential for the growth of 5G itself, and also use of 5G, application of 5G to help of these other industries and various social domains. Just Vishnu show the wish list for the next. So I certainly believe ITU will continue our challenges. And we really expect your continuous participation. So your contribution is essential.
So now we are really reach end of the this challenge, especially is now end of the year. So I wish all of you take relax, some pleasant time with your loved ones, loved families, and keep your health. And really wish to see you, all of you, at the next year, year 2021. Thank you very much. Back to you, Reinhard.
Yes, thank you. Thank you, Jessup. And with that, we are at the end. Thank you very much, everyone. Happy holidays, hopefully for many of you, for all of you. And that was it.
Thank
Gino,
you.
you will be playing the closing slides, Gino. All right. I think Gino is getting ready to play. Yes.